Experiment 16 in Chem 1212 is titled Paper Chromatography. In this experiment, we're going to explore the technique of chromatography, which involves separating compounds and characterizing compounds using a difference in their polarities. So in this introductory video, I'm going to do three things. First of all, I'm going to introduce the general idea behind chromatography and the big idea of separating by polarity, which is by far the most common separation technique that you see applied today. Secondly, I'm going to talk specifically about the technique of paper and thin film chromatography and how we measure and characterize the results of these experiments. And then thirdly, we're going to look at a chromatography simulator and see how changing the properties of the components of the mixture changes the result of a chromatography experiment. So let's begin with the general idea behind paper chromatography. So the overarching principle of all chromatographic separations is to separate on the basis of polarity differences. So in general, the way we separate compounds is we use differences in their properties and we exploit those differences to physically separate them in space. And the property that's most important for chromatography is the polarity of the molecule. So let's talk a little bit about this in general by looking at a general example of four compounds that are in a mixture, A, B, C, and D. And let's assume that A is completely nonpolar. So I've drawn sort of a non-existent dipole vector here that's just a point. That indicates that A is completely nonpolar. B, C, and D are polar and have permanent dipoles, and you can see that the dipole increases as we move from B to C to D. So there are polarity differences within this mixture, and you'll see that we can exploit these differences in a chromatography experiment to separate the components of the mixture. The basic apparatus of any chromatography experiment is really just a solid piece of paper or silica gel, any material on which the mixture can travel. This is called the stationary phase. For most types of chromatography, the stationary phase is some kind of polar surface. Because the surface of the stationary phase is polar, we can see that the four components of our hypothetical mixture will be increasingly attracted to this surface as we go from a very small or non-existent dipole to a very large dipole. So A will be very weakly attracted to the surface since it has no permanent dipole, while D will be strongly attracted to the surface because of its really strong permanent dipole. In fact, the only thing holding A close to the surface at all are van der Waals or London dispersion forces. Paper consists of cellulose, and in cellulose there are a number of hydroxyl groups, and each of these OH groups is of course highly polarized, so this gives you an idea of what the polar surface of paper looks like at the molecular level. To begin a chromatography experiment, we start with a dry piece of the stationary phase, dry piece of paper, and we apply to the bottom of it a spot of the mixture. So this spot that you see contains A, B, C, and D in some proportion. We then take that spotted stationary phase and we place it in a beaker at the bottom of which is a liquid that we call the mobile phase. Now, owing to capillary action of the mobile phase through the stationary phase, the liquid starts to move up the plate. And as it moves up the plate, the solvent carries soluble compounds in the mixture of A, B, C, and D up the plate. Let's assume, just for the sake of demonstration, that this is a non-polar mobile phase. After we allow the solvent to move up the plate, we'll end up with now a wetted piece of paper with four different spots on it, one for each of the compounds A, B, C, and D. And pay attention to the order here. Notice that the non-polar compound A, which we said was very weakly attracted to the polar surface, moves very quickly up the plate and is near the top of where the mobile phase reached. We call that the solvent front. B, which is slightly polar, is a little bit below A, C slightly below, and D even farther below. So what the results of this show us is that D is very strongly attracted to the stationary phase and relatively insoluble in the nonpolar mobile phase, while A, which is a nonpolar compound, is very soluble in the mobile phase and isn't really attracted to the stationary phase at all, so it moves very quickly up the stationary phase. So there's a push and pull here between two effects that dictate how far a compound will travel up a chromatography plate. On the one hand, solubility in the mobile phase encourages a compound to move quickly. So for example, A, which is nonpolar, is probably pretty soluble in the nonpolar mobile phase. like dissolves like. What's counterbalancing solubility in the mobile phase is the attraction of the molecule to the stationary phase. So D, for example, on the one hand, D is probably not very soluble in the nonpolar mobile phase because it's polar itself, and on the other hand, it's attracted strongly to the polar stationary phase. As a result, it's very difficult to push it up, and it tends to stay close to the bottom of the stationary phase even after we allow the solvent or mobile phase to move up. Transition to talking about how to measure the results of a chromatography experiment. So how do we take the visible results of a chromatography experiment, namely the plate and its spots, and translate that into quantitative information about how the experiment was run, and really the key question, which is how far did each spot travel? Well, let me introduce a little bit of terminology before we get into this. First of all, something I didn't mention that's very important is that we need to mark the initial position of the spot of the mixture that we added on the plate, and you see that in the bottom left here as a little black hash mark. You'll mark that in pencil at the start of a chromatography experiment. When the experiment is complete, the mobile phase or solvent will have moved a certain distance up the plate, and you'll want to mark that as well before the solvent evaporates and you lose that information. That point that the solvent reaches is called the solvent front. And the first variable that's important for capturing how far each spot traveled is the distance traveled overall by the solvent front. This is going to help us normalize the distances traveled by each spot because, of course, the absolute distances traveled by each spot are going to depend on how far the solvent front traveled in a linear sense. So we need to divide each distance traveled by each spot by the distance traveled by the solvent front. So for now, let's call that distance d sub SF for solvent front. To illustrate how far each spot traveled, we need to measure the lengths traveled by each spot, which is pretty logical. And we measure from that bottom left hash mark from the starting point of the spot to see how far each spot traveled. So for example, we could measure to the first spot, call that d sub A, second spot d sub B, and third spot d sub C. A couple of notes about these measurements. Notice that I've drawn the spots a little bit asymmetric. It's highly unlikely when you do chromatography at any point in your chemical education that you'll get spots that are perfectly circular. So to address this issue, we tend to measure from the center of the spot. It's most important to be consistent when you do this, and the general convention is to measure from the center of the spot, so be sure to do that in the laboratory. To communicate the distance traveled by each spot using a measure that's independent of the total distance traveled by the mobile phase, we use what's called RF, or retention factor. So the retention factor of spot A, for example, is the distance traveled by spot A, d sub A, divided or normalized by the total distance traveled by the solvent front, d sub SF, and RF of B and C are defined analogously. RF values are really important, and it's important to gain a sense of what they're telling you. A low RF value means that a spot stayed pretty close to the initial starting point of the spot throughout the chromatography run. This generally means the compound is very polar and is strongly attracted to the polar stationary phase. A high RF value indicates that the spot traveled very far and is up near the solvent front, and this indicates relatively weak attraction to the stationary phase and good solubility in the mobile phase. Notice that the distance traveled by the solvent front is the longest distance possible in a chromatography experiment, so RF values will range between 0 and 1. So to properly report a chromatograph, we need at least 3 different components. First of all, we need the identity of the stationary phase. For us, this will be paper, and you'll see this reported as something like on blank, on paper, on silica gel, on alumina, that kind of thing. Secondly, we need the identity of the mobile phase, something like 4:1 hexane to ethyl acetate. Now this 4:1 ratio is very, very important. When you get into the laboratory, you're going to start making solvent mixtures. It's a great way, in fact, to vary the polarity of the mobile phase kind of along a continuum. Add a little bit of ethyl acetate to the hexane to just slightly increase the polarity of the mixture until you get RF values that illustrate good separation. In other words, very different RF values. So you're going to be using solvent mixtures, and it's important so that someone can reproduce your experiment later on that you include the ratio of solvents that you used. And this is done by volume. So 4:1 means something like 40 milliliters of hexane to 10 milliliters of ethyl acetate. Finally, we need all the RF values for all of the spots observed. These 3 pieces of information fully describe a chromatography experiment. The stationary phase and mobile phase communicate the setup and the important experimental variables, and the RFs communicate the important results, namely the distance traveled by each spot. A quote-unquote good separation is one that involves very large differences in RF values, as large as possible. I'm going to just take a brief look at this chromatography simulation to show you how attraction to the stationary phase and solubility in the mobile phase work against one another to control how far a spot travels up the plate. So here we have a mixture of two components, one blue and one yellow. The mixture naturally is green, and we can control how strongly each component is attracted to the stationary phase. Here that's called adsorption to the paper being the stationary phase, and the solubility in the solvent, which is how soluble the component is in the mobile phase. So let's imagine that the blue compound is very polar, and we're again working with a non-polar mobile phase that you see in gray here down at the bottom. So that means that the solubility of the blue component is quite low, and its adsorption to the paper, which is a polar surface, remember those hydroxyl groups, is relatively high. The yellow dye, on the other hand, let's imagine that that is nonpolar, and so it's very weakly attracted to the paper, and its solubility in the mobile phase is relatively high. Notice how these two sets of properties are sort of the inverse of one another. Blue is high attraction to the stationary phase, low attraction to the mobile phase. Yellow is low attraction to the stationary phase and high attraction to the mobile phase. Watch what happens when I start the experiment. We see the mobile phase moving upward until it hits the initial spot. And now the yellow compound, which is very highly soluble in the solvent, is moving up at a much faster rate than the far less soluble blue compound, which is also strongly attracted to the paper. At the end of the run, we've got very good separation between the yellow compound and the blue compound. In practice, separations are rarely this easy. For example, imagine we used a polar solvent. Now the yellow compound, which was highly soluble because it's nonpolar, is now much less soluble, and its absorption to the paper is still low. Now the blue dye is much more soluble in the solvent we're using, but its absorption to the paper is still quite strong. Let's reset and watch what happens in this case. Again, the mobile phase moves up until it hits the spot. But now, because the yellow compound is relatively insoluble in the mobile phase, it's hardly moving at all. And the blue compound, which is strongly attracted to the paper, is sticking strongly to the paper even though it's also soluble in the mobile phase. So you can see that the blue compound is moving up a little bit, but the separation here is very bad. The RF values are very close to one another, and we still see a huge region of green where the compounds have not separated on the plate.